Hi, Assalamualaikum. My name is Hazirah binti Ismail. In this video, we'll be solving a metric problem using least square solution, Gram-Smith and QR factorization. The first one is find the least square solution of the linear system AX equal to B given by A is a metric 4 by 3 and B is a metric 4 by 1. Okay, first we need to find A transpose. Okay, using the given metric A, we can change that into an A transpose by taking this column and change it into a row, the first row. So the second column become the second row and the third column become the third row. So we get the A transpose. Okay, now we can find A transpose A. This is an A transpose and this is the A metric. So using a metric multiplication, we get the metric for A transpose A. Okay, next we find A transpose B. This is A transpose and this is B. Using the metric multiplication, we get the A transpose B metric. Okay, so now we can solve the system using A transpose A x equal to A transpose B. This system is actually an upgrade from AX equal to B. So, as you can see here, this system is actually can be solved using the usual method like Gauss Elimination, ARO, or LU Factorization. So, in this video, I would like to use Gauss Elimination. So, from this system, I would change it into an argument metric first, and then in the second row, I would like to change the first value 112 equal to 0, and for the third row, for the value 93, I will change it into 0. So in the second row, I will use this formula, and in the third row, I will use this formula. So now I get here equal to 0 and here also equal to 0. So next we will change this value equal to 0. Okay, to change this one, I need to use this formula. So after that, I get here equal to 0. So I get an upper triangular metric. Then the next step is I can do a back substitution because the first value I can find is actually an x3, and the second one is x2, and the last one is an x1. So I got the solution for the given problem using least square solution. Thank you.
Hi, my name is Nur Fatima Amira and I will show you how we can do least square solution, Gram-Smith process and QR factorization by using work from Mathematica programming. The first one is square solution. The equation is to find the least square solution of the linear system AX equal to B given by matrix A is 4 by 3 matrix and matrix B is 4 by 1 matrix. So the first thing we need to do in Mathematica is of course to define the matrix. So I name the matrix A the same as in the equation is equal to open parenthesis. To distinguish the column, we need to press Ctrl, comma. And to distinguish the row, we need to enter Ctrl, enter. Now that we have our 4 by 3 matrix, we can fill in our specific value, which is 27. And don't forget the semicolon. Semicolon here is used so that it will suppress the output. It is also used to separate two or more expressions. We will define our matrix B, which is 4 by 1 matrix, is equal to open parenthesis. Now that we have 4 rows, we enter the specific value. Now that we have defined our matrix, we need to find A transpose multiplied by A and A transpose multiplied by B. So to do that, we call matrix for comment. Matrix for comment is used so that the output will display the matrix in matrix form. Usually, Mathematica will display matrices in a list form. So if our matrix is a big matrix, the list will be very long and inconvenient to see. Bracket A transpose, we can call the comment transpose. Bracket matrix A, where we can also use the shortcut, which is A, matrix A, escape, TR, escape. We will get our A transpose multiplied by, in Mathematica, symbol of multiplication is just dot, multiplied by matrix A. Close the bracket, shift enter. Next, we calculate the multiplication of matrix A transpose and matrix B. So same as before, we call for matrix form. Shift enter, we will get our solution. We can compare our solution with the manual calculation that we already did before. Next, we can solve the system of A transpose AX equal to A transpose B to solve for X1, X2, and X3. To do that, we will do row operation, which in Mathematica, the command we have to call is just row reduce. This is the matrix that we will do row operation on. The left side is the matrix A transpose multiplied by matrix A, and the right side is the matrix of A transpose multiplied by matrix B. So I will define this new matrix as matrix S is equal to, open parenthesis, we now have 3 by 4 matrix. Now enter our values into the matrix. Close the parenthesis, semicolon, and enter. Now we just have to call for the command row reduce. Shift enter, we will get our answer here. So now we can see this is our X1, X2, and X3. So the answer for X1 is this, the answer for our X2 is this, and the answer for X3 is this. This is our final answer. We can compare it to our manual calculation. Thank you.
Hi, I'm Shazalia. Now I'm going to explain the Gram-Schmidt process to find the orthogonal basis and after that orthonormal basis for the column of matrix A. A equals to span column number 1, which is 2, 7, 4, 3 as x1, and column number 2, 6, 8, 5, 8 as x2, and column number 3, 9, 6, 3, 7 as x3. Now we let the vector number 1 is equals to x1 and partial basis x is equals to x1. Now we need to find our vector number 2, which is equals to x2 minus the projection of x2 onto the partial basis of x. This is the formula for the vector 2. Don't forget to pause the video to see the calculation. Now the final answer for vector 2 is equals to 122, negative 80, negative 29, and 144. Now we have two partial basis x. Thirdly, we calculate our vector 3, which is equals to x3 minus the projection of x3 onto the partial basis x. The final answer we get for the vector 3 is equals to 63,856, 15,041, negative 20,800, and negative 49,933. At last, we get our orthogonal basis is equals to vector number 1, vector number 2, and vector number 3 that we calculate before. For an orthogonal basis, we need to normalize at the end. Orthogonal basis, which is Q, Q1, Q2, Q3, and this is the formula to find the orthogonal basis. 1 over the magnitude of vector 1 multiplied with vector 1, 1 over magnitude of vector 2 multiplied with vector 2, and 1 over magnitude of vector 3 multiplied with vector 3. This is the formula for magnitude. The final answer for our orthogonal basis Q is equals to this. That's all from me.
Next, I will show you how we can do Gauss-Smith process by using Mathematica. The question is to find the orthogonal basis and after that orthonormal basis for column A. The first thing we need to do is to define x1, x2, and x3. So the command we call is matrix form. I name the first matrix as matrix 1, x1 is equal to curly bracket. We enter the element of the matrix which is 2, 7, 4, 3. Close the curly bracket and close the bracket. As you can see, I put dot after each element so that later the output will be displayed in decimal point form instead of fraction form. Shift enter, we will have our matrix S1 here. Same thing we do to define matrix S2 and matrix S3. Now that we have defined our matrix S1, S2, and S3, we can define orthogonal basis of vector 1 is equal to partial basis of S1. So to do that, we enter V1 is equal to S1. Shift enter, we will get our solution right here. Next, we will define orthogonal basis of vector 2, which is x2 minus the projection of x2 onto the partial basis of x. In Mathematica, we can just call the command of projection to solve this equation. So, vector 2 is equal to x2 minus the projection of x2 onto x1. Shift enter. This is our answer. We can compare with our manual calculation. We can find the orthogonal basis of vector 3, which is x3 minus the projection of x3 onto partial basis of x, which is x3 minus the projection of x3 onto x1 minus the projection of x3 onto vector 2. So we type in the command vector 3 is equal to shift enter. We will get our orthogonal basis of vector 3 here. Finally, we can solve for our orthogonal basis. In Mathematica, we just need to call for the command orthogonalize. So, I name our orthogonal basis as Q is equal to call for the command orthogonalize bracket, vector 1, vector 2, and vector 3. If enter, we will get our final answer. To see more clearly, we can display it in matrix form. Q/matrix form. Shift enter. This is our final answer for orthogonal basis. Thank you.
Assalamualaikum. My name is Wano Akila. So today I will solve X by using QR factorization. So we have our matrix Q here, where our matrix Q are orthonormalized vectors in the form of matrix 4 by 3. Okay, so this is our Q. Next, we need to find our transpose of matrix Q. Okay, so this is our Q transpose. Okay, after that we have to find our R. To find R, we have to multiply our Q transpose with A. Since our A is already been given, so we just multiply our Q transpose here with our A, and then we will have our R here, a 3 by 3 matrix. After that, we will have to find our R inverse. So to find our R inverse, we have to multiply R with identity matrix, and then we will have our R. Okay, this is our R inverse. And after that, we have to find our Q transpose and B. We have to multiply our Q transpose with B. So our Q transpose is a 3 by 4 matrix, multiply with B, a 4 by 1 matrix. So we will get the product of Q transpose and B is a 3 by 1 matrix. So this is our product of Q transpose and B. Okay, lastly, we will find our X by multiply our R inverse with the product of Q transpose and B. So we just multiply our R inverse and our Q transpose, our product of Q transpose and B, and then this is our final answer, where our X1 is 1.519862 and X2 is a negative 1.108465 and X3 is 1.070956. So this answer will be the same as in the Mathematica. Thank you.
To solve the problem given using QR factorization by Mathematica, the first step we need to do is define matrix A and matrix B. Okay, to define matrix A, we need to use this command. So this is our matrix A, and the second one is a matrix B, and this is our matrix B. Okay, then the second step is by using QR decomposition command, we can find Q transpose and R matrix. Okay, this is our Q transpose, and the second below is matrix R. Okay, the third step is we can recall Q transpose and R in a metric form. So we can type it like this. And this is our Q transpose, and this is for R metric. So the last one, we can just solve the value for X. Okay. That's all for QR factorization by Mathematica. This is our last answer, and we get the same answer as other method. Thank you.